This is Dr. Joshua Cooper, and this video is about anti-tachycardia pacing. We're going to discuss reentrant ventricular tachycardia and how pacing can be used to painlessly terminate reentry without resorting to painful ICD shocks. This video is nicely complementary to the one on entrainment pacing. In that video, we discuss how not to terminate reentry, but instead pace faster than the tachycardia to accelerate it and learn more information about the tachycardia circuit itself. But of course here, our goal is to terminate the reentry circuit, and we'll review how ATP works to accomplish this, as well as a new IATP algorithm that may improve upon previous ATP strategies. Let's first review the concept of reentrant ventricular tachycardia in the context of myocardial scar. If this represents normal myocardium, and these areas of dark gray represent scar, whether it's from previous infarction or a non-ischemic process, what we can see here are electrical barriers that are not excitable because it's fibrous tissue and not live myocytes, interspersed with areas of myocardium that is preserved. It's true that the conduction velocity may often be slow or the refractory period may be longer than normal, but as long as there's normal myocardium, then wavefront propagation can continue through the region of scar. Now, if there are two routes to get from point A to point B through the scar, separated by an electrical barrier, and if those two routes have slightly different electrical properties, then a beat may enter the region of scar, block in one direction, and travel around the other, and that can initiate reentrant tachycardia. Here is that potential reentrant circuit, and if all of the cells throughout the circuit have refractory periods that are shorter than the conduction time that it takes to get around that circuit, then you can sustain reentry. Think of it as an arrow that can revolve around the circuit where the head of the arrow doesn't catch the tail. The region in between the head and the tail of the arrow is known as the excitable gap. Those are myocytes that have recovered, ready to be depolarized by the oncoming wavefront. And while that's occurring, then the tail is receding. Those cells are recovering and are now excitable. And so that excitable gap is going to revolve around the circuit at the rate of the ventricular tachycardia. Now, if we have a lead in the heart and we wish to interact with the VT circuit itself through pacing, then we had better create a pacing stimulus that sends a wavefront to the VT circuit and hits excitable tissue, denoted here as green. That was the excitable gap we just discussed. However, the ventricular tachycardia and the excitable gap are rotating around that circuit. And so you'd better have a very well-timed beat if it is to hit the circuit at a favorable moment when the excitable gap is facing the oncoming wavefront. If instead we pace and that wavefront hits tissue that's refractory, here denoted in the yellow arrow, then we will extinguish that wavefront and not affect the tachycardia whatsoever. That will continue to rotate uninterrupted. If instead we send a pacing stimulus wavefront toward the tachycardia at a favorable time that the excitable gap is facing us, we will be able to interact with the circuit. In this case, we send a wavefront to the tachycardia and hit the excitable gap at its back end, near where the arrowhead or the oncoming wavefront is approaching. As we hit excitable tissue, we'll be able to then propagate wavefronts in both directions, forward and backward. The backward or retrograde wavefront is going to collide with the oncoming tachycardia wavefront and extinguish. The anterograde wavefront will travel forward, and if we're at the back end of the excitable gap, then that forward wavefront will not reach refractory tissue, but instead will launch a new reentry beat around the tachycardia circuit, just as the VT would had we not paced. Here's the tachycardia continuing, following that paced beat, which excited tissue at the back end of the excitable gap. Now, what if we send a wavefront and we hit the front end of the excitable gap? Again, we hit tissue that's excitable, and again, we send wavefronts in both directions. Here, the retrograde direction will hit the oncoming wavefront and extinguish, but now, because we are close to the tail of the arrow, we are close to refractory tissue, then the wavefront that we launch in the forward direction may then extinguish because it hits refractory tissue and is unable to propagate. And now in this scenario, we've terminated the reentrant tachycardia because we've reached refractory tissue in both directions, and there is no wavefront that is able to continue propagating around the circuit. This is how anti-tachycardia pacing works, and the entire goal of ATP of any scheme. We're trying to get a single beat into the excitable gap near the front end of the gap, meaning near the tail of the arrow, where tissue is refractory, and will hit refractory tissue in both directions, thereby extinguishing the tachycardia circuit. Now, the chance that a single pacing pulse is able to get into that excitable gap at exactly the right place and time to extinguish VT is very small. It's far more likely that a single pacing pulse is going to hit refractory tissue, as shown here. So if we have any chance for ATP to work to terminate VT, we're going to have to give multiple pacing pulses and hope that one of them hits the excitable gap at the right place and time to extinguish the VT, as I showed before. If we paced at exactly the same rate as the VT and the first beat didn't work, then every subsequent beat is also going to hit refractory tissue at the wrong place and time. And so for ATP to work, we have to pace faster than the VT cycle length so that the excitable gap is at different locations with each subsequent pacing pulse. Here we're going to demonstrate that principle, and you'll see with each paced beat, the excitable gap is slowly marching backwards relative to our oncoming wavefront until the time comes that we hit excitable tissue. And if we approximate just faster than the VT, our cycle length of pacing, then we're likely to hit the back end of the excitable gap. The retrograde wavefront that propagates will extinguish, and the forward wavefront is going to launch another reentrant VT beat. But the challenge of pacing and hitting the excitable gap is not just limited to the location of the excitable gap around the circuit relative to our pacing location, but in addition, because the VT is revolving and sending wavefronts toward our pacing lead, the tissue between the lead and the circuit is also going to be refractory because of the preceding ventricular tachycardia beats. And we're going to have to compete with that oncoming wavefront that continues to propagate toward our lead. So in order for us to pace and get into the excitable gap, not only do we have to hit the excitable gap at the right location, but we have to first overcome the oncoming wavefronts that are propagating toward our lead. And if we pace faster than the tachycardia, then the collision location with each subsequent paced beat is going to get closer and closer to the circuit until we finally get to the circuit and enter the excitable gap, sending wavefronts in both directions around that circuit. So how many pacing pulses does it actually take in order to overcome the VT wavefronts that continue to bombard the tissue between the pacing site and the circuit? Well, that's largely going to depend on the electrical distance between the pacing site and the entry of the VT circuit. So for example, if the electrical distance is 150 milliseconds, then we're going to have to reclaim that amount of time with sequential pacing pulses in order to claw our way toward the circuit. And it's going to depend on how much distance we gain with each pulse, how many pulses it will take in order to traverse that distance. So for example, if this represents the incremental gain that we have achieved with one pacing pulse, then it's going to take this number of pacing pulses to add up to that electrical distance between the lead and the circuit in order to enter the excitable gap. Now, if we happen to be a little bit further away from the circuit with our pacing site, and we're able to reclaim about the same amount of time, meaning distance, with each pacing pulse, then we're going to need more pacing pulses in order to get to the circuit and start to impact the ventricular tachycardia circuit itself. Alternatively, if you have a fixed electrical distance, but you reclaim less territory per pacing pulse, then it's going to again take you more pacing pulses in order to traverse that distance and get to the circuit and start to interact with it. The two scenarios where this is true are if you pace at a higher percentage of the tachycardia cycle length, meaning there's less difference between the tachycardia cycle length and your pacing cycle length. For example, if you're pacing at 91% of the tachycardia as opposed to 81%, where you're pacing faster, you have a shorter cycle length, and you're going to reclaim more territory per pacing pulse. Additionally, at faster VTs, where you have a shorter cycle length to begin with, a fixed percentage of that cycle length will translate into a smaller increment of time. So if you have enough beats in a row where you're able to gain territory with each beat and get to the circuit and then start to interact with it, this is what that would look like. Here are a series of pacing pulses that are getting you closer and closer to the circuit until a point comes that you actually get to the circuit and interact with it. And in this scenario, if we continue to pace at exactly the same cycle length, and we keep hitting the excitable gap near its back end, then the forward wavefront that we launch is not going to terminate the VT, but instead is going to entrain it. Another term for that is continuous resetting. So if you pace at a single cycle length, you get to the circuit, and then you continue to entrain it, then you're not going to terminate the VT, you're just going to accelerate it while you're pacing, and then when you come off pacing, the VT will resume its previous cycle length. So let's turn our attention to how successful anti-tachycardia pacing would work with the intrinsic ATP algorithm. This algorithm is designed to deliver a series of S1 pacing pulses at a certain cycle length, and then deliver an S2 pacing pulse that's shorter than S1, and the purpose of the S2 is to try to hit the excitable gap at exactly the right location, at the front end where it will extinguish in both the forward and the backward directions, thereby terminating the VT. So here's this S1, S2 concept where it works perfectly. Here's tachycardia revolving. We deliver a series of S1 pulses, and then an S2 pulse that terminates the tachycardia. And let's review, because I know that went by quickly, what happened with each of these 6 S1s and that single S2 beat. In this cartoon, the first 4 S1s were those that reclaimed the territory between the pacing site and the tachycardia. None of them affected the tachycardia, but gradually they got the wavefronts to propagate closer and closer to the circuit. The next 2 S1s in this example got to the excitable gap, but they were not early enough to terminate the VT, but instead they entrained it, launching new wavefronts each time. And then the S2 beat was delivered at exactly the right moment, so the excitable gap was further back, and we hit it at the exact location where the forward wavefront catches the tail of the previous beat, thereby extinguishing that direction, and of course the retrograde wavefront hits the oncoming wavefront and also extinguishes, thereby terminating the VT. Let's review a scenario where the S2 pacing pulse fails to even reset the VT. Here we are pacing during tachycardia, delivering some S1s and then an S2, and the VT is continuing. Let's break this down and see what happened. First, the S1 beats, and here there were only 3, insufficient to get to the circuit, partially reclaimed the territory between the pacing site and the circuit, but didn't quite make it there. And then the S2 beat collided with the oncoming wavefront closer to the circuit, but it wasn't early enough to get into the excitable gap or affect the tachycardia either. So in total, none of the beats ended up getting to the circuit, none of them reset the tachycardia, and certainly it did not terminate the tachycardia. So in order for this pacing train to be successful, we would have had to deliver more S1 beats to reclaim more territory to get to the circuit to allow that S2 beat to penetrate the excitable gap and extinguish the tachycardia. Here's another scenario where we fail to terminate VT, but instead the S2 beat resets it. Again, we're going to deliver pacing pulses, a series of S1 beats and an S2 beat, and the tachycardia continues. Let's break down this scenario. The first 4 S1s successfully reclaimed territory to get to the circuit. The next 2 S1s were able to penetrate the excitable gap and launch new wavefronts and training the circuit for those 2 beats. But the S2 beat hit the excitable gap a little too far back to hit refractory tissue in the forward direction, and it also entrained the tachycardia, launching another wavefront, accelerating it but not terminating it. In this scenario, if we were to have terminated the tachycardia, that S2 beat would have needed to be a little bit earlier so that the excitable gap was a little bit further back and that forward wavefront reached refractory tissue. Here's yet another scenario where we failed to terminate VT, and here it's because the S2 beat failed to capture tissue. And here's that scenario. We have a series of S1 beats and then a rapid S2 beat, and the tachycardia continues. And let's break this one down and see what happened. In this case, the first 4 S1 beats reclaimed the territory just as before. The next 2 S1 beats accelerated the tachycardia by entraining it. And the S2 beat, unfortunately, was delivered so early that it hit refractory tissue. It didn't propagate at all to get to the circuit. So if we were to alter this anti-tachycardia pacing scheme in order to try to terminate VT the next time, the S2 pulse would have to be later so that it actually came at a time that the tissue was excitable. And then we could add an S3 a little bit faster when the tissue had a little shorter refractory period in order to penetrate into the excitable gap at the right place and time. So let's review 4 anti-tachy pacing scenarios where we deliver S1 and S2 beats. The first, of course, is success, where we deliver enough S1s to get to the circuit and start to entrain, and the S2 beat is able to hit the excitable gap and terminate the VT. The second scenario that we just reviewed was where the S2 beat didn't even reach the circuit and failed to reset. The third scenario, the S2 beat got to the circuit, got in the excitable gap, but wasn't early enough to terminate, but instead also reset the VT like the last S1 did. And then the last scenario is if the S2 comes too early so that it doesn't capture myocardial tissue because it's refractory. So in these 4 possible outcomes of an S1, S2 delivery scheme, only the top left results in success and the ATP algorithm no longer has to deliver any pacing. But in the other 3 scenarios, the VT is ongoing, and the algorithm then has to decide what it needs to do in order to be successful. And again, to review, in the top right scenario, in order to succeed, you'd need more S1s in order to get to the circuit with that S2 beat. In the bottom left scenario, we need to deliver an earlier S2 in order to terminate by hitting the excitable gap at a more favorable location. And in the bottom right scenario, where we didn't capture, we need to have the S2 beat later and then add an S3 beat in order to have that last pulse get to the tachycardia at the right place and time to terminate VT. So the logical next question is, how does the algorithm know which of those 3 failed scenarios occurred so that it knows how to alter the pacing scheme in order to succeed the next time? And the answer comes in the period of time between the last delivered pacing pulse and the first VT beat that is sensed by the device when the VT is ongoing. This is known as the post-pacing interval, and it is a common concept in the EP lab when we perform entrainment or pacing maneuvers during any type of tachycardia. Here is anti-tachy pacing delivered by a device, and here is the ongoing VT that failed to be interrupted by the ATP. And here is the post-pacing interval between the last paced beat and the first beat of VT as it resumes. So let's think for a moment of what's actually happening at that interface between that last paced beat of the ATP sequence and the first VT beat that sends a wavefront back toward the lead to be sensed by the device. And let's think of this scenario where that last anti-tachy pacing beat entrains the tachycardia but does not terminate it because it hits the excitable gap too far back. Here is that last paced beat. It gets into the excitable gap. It launches another wavefront around the circuit, which then propagates back toward the lead. And then, of course, the VT continues uninterrupted, sending ongoing electrograms back to the lead as the VT continues at the same cycle length that it had prior to ATP delivery. If we break down that interval between the last beat of ATP and the first beat of ongoing ventricular tachycardia, we're going to see that several events occur during that post-pacing interval. Again, in this case, if the last beat entrained the tachycardia. What's going to happen is we send a wavefront to the circuit. It travels around the circuit to the exit and then back to the lead. And if we break that down into its temporal components, we're going to see that the total post-pacing interval time is composed of the electrical time it took to get to the entrance, the time it took to revolve around the circuit to the exit, and then the amount of time it took to get from the exit back to the lead. And therefore, the post-pacing interval is the sum of the tachycardia cycle length plus 2 times the electrical distance of getting to and from the circuit. They're not exactly the same depending on the distance to the entrance and the distance from the exit, but overall that's the rough amount of time you think about when you entrain tachycardia and have a return beat come from the ongoing interrupted VT. Now let's repeat that exact same type of temporal breakdown of the post-pacing interval in the 3 different scenarios where ATP fails to terminate VT. And this first scenario is that failure to reset, where the S2 beat doesn't even make it into the entrance and doesn't affect the tachycardia because it hits refractory tissue before it gets there. So the first step at that last pacing beat is a wavefront is launched toward the VT and it blocks right before the entrance. While it's doing that, by the way, the VT continues to revolve partway around its route. At this point, the VT continues to revolve and it reaches the exit site, which is refractory because of the pacing beat that just occurred. And so the VT has to revolve one more time around its circuit to get back to the exit and find now tissue that's excitable and able to launch a wavefront back toward the lead to be sensed by the device. If you look at these steps, you're going to see the sum total is going to be a longer post-pacing interval. And we're going to use this yardstick here at the bottom to show the 3 zones and how they're going to be interpreted in terms of what must have occurred with that last pacing pulse. Here, a long post-pacing interval signifies a failure to reset. In the scenario where the S2 beat resets the tachycardia because it gets into the excitable gap but not far enough forward, here's what happens. That last paced beat gets to the circuit. It excites tissue in the excitable gap, having entered at the entrance site. The tachycardia will revolve around 1 revolution to get to the exit, having been slightly advanced, by the way, by that last pacing pulse. And then the wavefront will launch back from the exit site toward the lead to be sensed by the device. We reviewed this earlier, and that'll give you an intermediate post-pacing interval time period, and it falls in this reset zone, which again we're going to review shortly. In this third scenario, where the S2 beat loses capture altogether, here's what happens during that post-pacing interval. That last paced beat is refractory, and so nothing happens. There's no depolarized tissue between the lead and the circuit. Wherever the VT wavefront happens to be will continue to revolve toward the exit. And the exit, of course, is available because we hadn't depolarized tissue between the lead and the circuit, and so that wavefront will propagate back to the lead to be sensed by the device. And here we're going to have a short post-pacing interval that falls in this loss of capture zone on our yardstick, because we didn't even have a full revolution of the VT, and it was able to immediately exit and get back to our lead after that last pacing pulse failed to capture altogether. So let's again review those three scenarios, now in the context of how the IATP algorithm thinks about the post-pacing interval when VT failed to terminate with an ATP sequence. If you have a really long post-pacing interval, that would tell us that we fell into that failure to reset zone, meaning the S2 never made it to the circuit. And so the algorithm will add S1 stimuli for the subsequent anti-tachy pacing scheme. That will allow us to reclaim that territory and have the S2 enter the excitable gap with a chance to terminate VT. If the post-pacing interval had an intermediate duration, that tells us that we fell in the reset zone. The S2 beat made it into the circuit, but it didn't terminate, but instead advanced that last beat. That means that the S2 didn't come early enough, and it needs to be shortened for the next ATP scheme. And in addition, the algorithm now knows that it successfully had enough S1s to get to the circuit and allow the S2 to penetrate and advance the VT. And so it can recalculate using that formula we alluded to before, that the post-pacing interval, when you've reset the tachycardia, includes 2 times the electrical distance, meaning the time to get to the circuit and the time to get back, plus the tachycardia cycle length itself. So it can roughly calculate the electrical distance and recalculate how many S1 beats it actually needs to get to the circuit and not provide excessive S1 beats, which potentially could only serve to trigger another VT circuit, for example, which we'll talk about in a moment. So you could see, if you fall in this zone, not only a shortening of the S2, but a reduction in the number of S1 stimuli in the subsequent scheme. And lastly, if you have a really short post-pacing interval, meaning that last paced beat failed to capture altogether, that tells the algorithm that you had loss of capture, and how it will behave is to lengthen that S2 so it captures and add an S3 beat so that that last beat can hopefully penetrate the excitable gap at the right moment and terminate the ventricular tachycardia. There's actually a fourth reason that ATP may fail in addition to the 3 we've discussed. We've been focusing on scar, a barrier, a circuit, and the revolution of the excitable gap. But we need to also remember that this circuit exists in the context of myocardial scar that will have other areas where there are potential circuits. So if anti-tachy pacing is delivered, and even if it terminates VT, or let's say it doesn't, then those pacing pulses are going to get elsewhere into the scar and potentially find and initiate another VT, which could be faster or slower than the tachycardia that was being targeted. If this occurs, then the algorithm will need to start over again because we have a new tachycardia cycle length, and the IATP algorithm will have to recalculate the number of S1s and the S2 cycle length, and then it will start from scratch with this new VT. Here's an example of that occurring with a traditional ramp ATP algorithm, where we have VT1 here on the left. A ramp ATP is delivered. VT does not terminate, but it's a different electrogram and a different cycle length. And again, if this were to occur, the IATP algorithm would recognize the different cycle length, and it would start over again in its algorithm in an attempt to terminate this new ventricular tachycardia. So let's review what we've learned when thinking about reentrant VT and how anti-tachycardia pacing works or doesn't work to terminate the VT. Of course, the main goal of ATP is to terminate VT painlessly and avoid painful, unnecessary shocks that decrease quality of life and cause psychological harm to the patient. Standard burst and ramp ATP schemes essentially are brute force attempts to terminate VT, and it's a bit of trial and error whether either one of them is able to deliver pacing pulses into the excitable gap at the right place and the right time to terminate VT. A less aggressive burst pacing delivery may not have enough pulses to even reach the circuit, or if it does, it may continue to reset the VT and entrain it at that same pacing rate, but not terminate it. A more aggressive burst or ramp pacing scheme may miss the excitable gap because the beats that reach the circuit come too early at the wrong time to get into the excitable gap, and or you may fail to capture tissue because the last pacing beat or beats meet refractoriness at the location of the pacing site or between the site and the circuit. And in addition, if you deliver too many pulses or pace too quickly, you could initiate a different VT. The purpose of IATP is to try to deliver just the right number of S1 stimuli and deliver an S2 at exactly the right moment, so the ATP scheme acts like a very precise sniper to deliver one pulse at the right time to terminate VT, thereby reducing the chance of accelerating into another VT because you don't deliver too many pulses or pulses that are too fast, and you learn why you failed in the last ATP scheme to improve the next time.